So welcome to the video lecture series on Introduction to Computer Networks, and this is part 2 of our topic on Ethernet LAN. So we will jump off to the point where we left off, and so here we go. So the layer 2 Ethernet LAN protocol has a frame which has a structure which looks like this, where the first 8 bytes is what we call the preamble. The reason why we have it as 7 plus 1, I will explain it in just a little bit. The next 6 bytes is going to be our destination address, and the 6 bytes after that is the source address. Both of these addresses are 6 bytes in the form of MAC addresses. The next 2 bytes is a field that we call type, and this can refer to different types of Ethernet LAN addressing, and it could be an IPv4 Ethernet frame packet or an IPv6, and there are other forms as well, but these are the most common two ones, the two most common ones. The next field is the data field, which is basically the protocol data unit from the upper layer, that is the network layer, and it ranges from 46 to 1500 bytes. The reason you see here it says that it is with a padding is because it has to have a minimum of 46 bytes. So if the data from the upper layer is less than 46, it will add some padding to make it a minimum 46. And the maximum data that it can have is 1500 bytes. Finally, the last 4 bytes is what we call the file sequence check, and this is an integrity checking mechanism that Ethernet frames have. So if we look at the preamble, which is a total of 8 bytes, the first 7 bytes are 56 bits. It is of alternating ones and zeros. So if you see here, so it's 1010, and it will go on for 56 bits. And finally, the last byte, that is the last 8 bits, it's going to be 6 alternating ones and zeros followed by 1, 1. So this breaks the pattern of the previous 7 bytes of alternating ones and zeros, and this is when the frame tells that this is a starting point for the destination MAC address. So the start frame delimiter, which is the last 1 byte out of these 8 bytes, is what we call the SFD, and this marks the end of the preamble and the beginning of the destination MAC address. The data field, we have already mentioned that it contains the data from the upper layer and is a minimum of 46 bytes and a maximum of 1500 bytes. And the padding is required if the data from the upper layer is less than 46, so that the total comes to be 46 bytes. Finally, the frame check sequence, the FCS, is a total of 4 bytes, and it allows us to detect corrupted data which might have gotten corrupted during the time of transmission. This is a mathematical function which takes in the input of the source and destination MAC addresses, the length data type field, the upper layer data, and the padding together. All of these are put into the mathematical function, and it spits out a value which is then included in the FCS field. So the MAC address format, something we have looked at in our previous topic as well, it is a 48-bit address which is equal to 6 bytes, and it's generally represented in 12 hexadecimal digits. The format usually is created in the way that the first 6 hexadecimal digits is referred to as the organizationally unique identifier, and the next 6 hexadecimal digits is specific to that hardware device. So for example, if Dell is manufacturing a network interface card or NIC, the MAC address for that network interface card would start with 5C260A followed by 6 hexadecimal digits, which is specific to that device. And that is how MAC addresses are created, and they are very specific to the hardware. And this format applies to both the source and destination MAC addresses. So in the process of transferring data over an Ethernet LAN, a switch needs to know how it should be forwarding a frame from a source to a destination. So this decision process that the switch needs to go through is what we call switch forwarding. And this is done with the help of determining the destination MAC address and the outgoing port. So with respect to this, there's something that we call MAC address table, and this is applicable for all switches which are placed in an Ethernet LAN. So let's say a source sends a frame over to a switch which has a destination mentioned in the example here as 0000.2222.2222, and the switch then looks it up in its MAC address table and finds that this destination can be reached if the frame is forwarded out through port FA0/2. So the switch forwards the frame onward through that port. So the basic logic here is that the MAC address is looked up, the destination MAC address is looked up in the MAC address table, and the frame is forwarded. If there's no entry, it doesn't do so. So let us consider a scenario where there are multiple hosts and all of them are connected to a single switch. So in this case, there are 6 hosts and all of these are connected to a single switch in ports 1 through 6. So whenever a frame receives one of these frames, they buffer the packets, and the incoming link is something which is known with respect to the source destination. So in an example where A is trying to send out something to A prime and B is sending something out to B prime, they can transmit simultaneously without collisions because these are what we call independent collision domains. And in the process of this transmission, if you try to understand how does the switch know that A prime is reachable through interface 4 and B prime is reachable through interface 5, the process in which it generates this is called learning, and the eventual result is what we call a forwarding table. And the entry over there has the MAC address and the interface that it needs to forward each host, and also a timestamp to keep track when that record was obtained. So this looks something similar to what we call a routing table, and we will also look at in the next part how this forwarding table is generated in the process of transferring frames across different hosts through the Ethernet LAN.